Welcome everyone to week 3. This week we are going to look at more advanced and state-of-the-art CNN architectures, as well as discuss how we adapt these networks, which were originally designed for 2D natural imaging datasets, to work for medical imaging. The goal of this week is to put into context recent developments in the field by reviewing historical development of CNNs from ResNet in 1998 to more recent networks, in particular ResNet and variants of UNet, which remain a backbone of prediction and segmentation networks respectively. Here, ResNet was the first to propose use of residual connections to improve generalization of very deep networks, and UNet was the first segmentation network to propose symmetric encoder-decoder architecture with skip connections. We will look at the impact of changing network depth or width, or the input resolution, and the interactions between each. In Monday's tutorial, we will then explore implementing ResNet and UNet from scratch, and we'll look at saving networks at regular intervals. This will probably prove very useful for your project. On Thursday, we will then explore adapting network design and pre-processing to support deep learning with medical imaging data. Medical data has very specific constraints, which mean that networks designed for natural image data should not be expected to work out of the box for medical images. It's important to know the challenges, what can go wrong, and why. As part of this, we will first explore generic pre-processing strategies and general approaches for training with small datasets, specifically data augmentation and regularization. In Thursday's tutorial, we will then review pre-processing and training techniques largely specific to medical imaging, including augmentation with B-spline constrained nonlinear deformations, pre-processing through histogram normalization, patch-based training to reduce input size and simulate the presence of more data, and alternatives to batch norm, where this is necessitated by memory constraints, which significantly constrain the possible batch sizes for large images. But let's start with a quick recap of the important concepts from last week that you must bear in mind going forward. Convolutional networks have been designed to take inspiration from biological networks in order to support efficient and effective deep learning on images. The idea is that rather than treat each pixel or voxel in an image independently, which is in any case not realistic given known image properties, instead CNNs learn a hierarchy of filter kernels which learn to detect increasingly complex textures and objects in each image. Thus, neurons in CNNs have only very local connectivity, just to the image locations which overlap with the feature kernel. But all neurons are forced to parameter share, in other words, learn just one consistent filter per output channel. This thus reduces to a convolutional operation. The weights tensors for CNNs therefore have shape output channels by input channels by filter dimensions, which are typically consistent in each of the directions. When compared to the weights dimensions of an equivalent fully connected layer, which connects to every height, width, and depth location in the input, this significantly reduces parameters. Note that without padding, a convolutional layer would return objects with reduced dimensions relative to the input, since it can only return a value at locations where the filter can be centered. This is typically undesirable, so padding adds layers of zeros to the outside of the image to prevent this. CNNs do, however, need to implement downsampling so as to increase the receptive field and thus capture range of filters, suiting them to detection of ever larger and more complex features of the image. However, this is implemented through pooling or striding. Thus, some important things to consider when designing architectures are first, increasing CNN network depth can be worthwhile, as it allows the network to learn filters of increasing receptive size, as well as increase the expressivity of the features learned. More layers, however, means more parameters, and thus longer training, and for small datasets, which is always the case for medical imaging, overfitting. So we've already seen some strategies for combating this. For example, use of one-by-one convolutions to reduce the channel dimensions in so-called bottleneck layers, batch normalization to stabilize and speed up training, dropout for regularization. However, we will look at more strategies this week, specifically residuals. Another important trick that we learned was switching fully connected layers for convolutions, where if filter dimensions equal the shape of the input, this will also return a 1D vector. However, the point is that it allows for testing on inputs with different sizes to the training data, and even more importantly, it allows for upsampling the bottleneck back to the original image dimensions, which supports semantic segmentation. After that, we looked at loss functions and optimizers. What we ideally want from a loss is for it to be smooth and convex, and to distinguish strongly between slightly wrong and very wrong answers. This can typically be fulfilled for a single neuron loss, but for networks which combine millions of parameters, it becomes much less likely to see. For example, here, and in last lecture, we showed an example of the VGG loss landscape, which was one of the first big CNN architectures. What we'll see this week is that architectures evolved, most notably through the design of residual connections, which combined with batch norm worked to smooth the loss landscape and in that way support much deeper networks. So for example, this is a ResNet, which was the first to implement residual connections, and DenseNet took that concept one step further. In terms of optimization, typically networks are trained either with stochastic gradient descent with momentum or with ADAM, where ADAM supports adaptive learning rate tuning on a per parameter basis and trains much faster, but sometimes doesn't converge to as good a minima as SGD. So sometimes it can help to switch from ADAM to SGD towards the end of training. Finally, a quick recap of implementation in PyTorch. So the convolutional layers will take as argument the input and output channel dimensions, the kernel size, which will generally be an int for filters with equal dimensions, but it could be a shape tuple, for example 3, 5, if not. The next argument is the stride. Now this only needs to be greater than 1 if it is your intention to downsample through strided convolutions. Padding, which should be, for example, 1 to output a same convolution for a 3x3 kernel and 2 for a 5x5 kernel. Next, looking at batch norm. So this just needs to know the number of channels it's going to receive. And dropout, which doesn't really need any definition of input arguments unless you want to change from the default dropout rate, which is the percentage of activations dropped each time. Loss functions also don't often take parameters, although they will, of course, if you need to pass a weights tensor. In that case, either the tensor or the loss will need to be passed to the device when performing GPU training. Optimizers, on the other hand, do expect arguments. You must pass the network parameters, and in these notebooks where we are training several networks, do make sure that you are passing the parameters of the correct network. It will also take a learning rate and, if desired, momentum parameters, which may be tuned during optimization. But now let's get started on this week's content. We will begin the week by looking at CNN architectures, starting with historical development of CNNs from the first ever example, LeNet, developed by Jan LeCun in 1998, through AlexNet, the network which started the most recent revolution in deep networks for image processing in 2012, to more recent landmark methods such as ResNet for classification or regression, and in the next video, UNet and other segmentation networks. Relative to what we've seen before, these latter approaches go beyond simple stacking of convolutional blocks to now implement networks featuring skip connections, residuals, attention blocks, and spatial transformers, for example. Note, from now onwards, it will be very important to train our networks with GPU as images and networks are getting much bigger. So, starting first with LeNet, this was the first convolutional network trained for MNIST classification. Back in those days, computer memory was much less powerful, networks therefore had to be much smaller. The CNN revolution towards intelligent, biologically inspired networks was therefore a pivotal development, as it allowed deep networks to be built with far fewer parameters than fully connected networks, and therefore to train and generalize on proportionately, by today's standards, small imaging datasets. The LeNet architecture involves two convolutional layers, each separated by one average pooling step. The third convolution then flattens the result with a 5x5 filter operation applied to a 5x5 input stack so that it can be passed through two linear layers and a final softmax operation. Interestingly, unlike modern CNNs, LeNet does not utilize filters with depth equal to the full depth of the incoming activation, and this was due to computational constraints. The next network we will look at is AlexNet. This jumps forward to 2012, where, supported by vastly more powerful GPU computing and enormous natural image datasets, the deep learning revolution finally took off. So AlexNet involved 5 convolutional layers and 3 linear or fully connected layers. Unlike LeNet, which used tanh activations, AlexNet used ReLU for the first time. Downsampling was still performed with pooling operations, but in this case, max pool. One considerable factor in AlexNet's success was ImageNet. This was a huge dataset of 15 million labelled high-resolution colour natural images belonging to 22,000 categories, collected from the web and labelled with categories through use of Amazon's Mechanical Turk crowdsourcing tool. This was an initiative led by the prominent Stanford professor Fei-Fei Li. Other design choices which contributed to the performance of AlexNet included use of data augmentations. These, which we will discuss in session 2, are transformations of the data made to simulate the appearance of more examples. So in this specific case, it involved translations and crops, horizontal reflections, and PCA-based intensity variation. The authors also added dropout for the fully connected layers, trained with batch SGD with momentum, and used weight decay, otherwise known as regularization, which again we will look at more detail in Thursday's session. Relative to LeNet, this network represents a significant jump in parameter size from 60,000 to 61 million parameters and was made trainable by the huge size of ImageNet. Moving on now to VGGNet from 2014. This network increased depth whilst conserving the number of required parameters by stacking together layers of smaller 3x3 or 1x1 kernels in place of the larger 7x7 or 11x11 ones used by AlexNet. Doing so had the effect of approximating or simulating the behaviour of these larger filters at the expense of fewer parameters. Greater number of activations increased the capacity of the model to learn more non-linearities, thus making the network more discriminative and supporting better performance. Unfortunately, greater depth came at the expense of slower training. At the same time, GoogleNet, or the Inception architecture, was proposed, incorporating similar ideas, seeking to reduce total network parameters by instead learning convolutional filters over a hierarchy of scales at each level, stacking together outputs of all operations to feed into the next layer. So specifically in this example from the first Inception model, the network architecture learns both 1x1, 3x3 and 5x5 convolutions at each layer, also offering the option of a max pool without stride instead. In this way, the network becomes both wider and deeper. Why should this help? Well, the idea is motivated by the fact that we expect that salient parts of the image will vary in how much of the image they take up. For example, an object might be close up or far away. This creates a scaling problem where choosing the right size kernel for the convolutional operation becomes tough. Deeply stacked networks can learn to be invariant to scale, but they do so at the expense of increasing the number of network parameters, which encourages overfitting. So the Inception approach was instead to train several filters of different scale with the view of allowing the network to detect features over many scales at each level, thereby reducing the number of parameters required to achieve this goal relative to networks learning a single size kernel at each layer. The problem with it is that a naive implementation of this architecture instead increases network parameters. Thus, to get it to work, they therefore needed to insert one-by-one convolutions before the larger kernels, where these merge activations and therefore reduce the channel dimensions, and hence reduce the number of parameters needed to be learned overall. In this way, they were able to reduce the required number of parameters for the inception network from 854 million to 358 million. So the full network for Inception 1 then have 9 inception modules stacked one after another with an average pool instead of a fully connected layer directly after the last convolutional layer. They also placed 2 auxiliary classifiers, 1/3 and 2/3 through the network, and this was to counteract vanishing gradients. However, one of the most impactful papers of recent times was ResNet in 2015. These networks make clever use of skip connections to learn very deep networks which generalize much better than previous networks. For example, you should see that the error of these ResNets when compared to equivalent networks without residual layers is much lower. The motivation for residual network design comes from resolving the following contradiction of deep networks, where in principle adding additional layers shouldn't make performance any worse because a network should be able to learn to ignore them. However, in practice, this doesn't actually happen, leading to overfitting. So the ResNet solution to this was to incorporate a skip connection, which instead directly maps the identity transform around weights layers to add it to the output of the residual block. So in other words, it's taking a copy of the input and mapping it round the outside of the weights layers and adding it back on again at the end. This means that these networks are instead learning a residual mapping. F of x equals h of x minus x. Where f of x here is what is being learnt by the weights layers, and x is equal to the input and therefore represents the identity mapping. So the combination of h of x, which is equal to f of x plus x, is what the residual block is outputting. And this means that f of x is just learning the residual of what is required after we take away the identity. The reasoning being that it is actually much easier for a network to push this residual to 0 than it is for it to learn an identity mapping through a combination of complex nonlinear interactions. Note, importantly, there are several versions of ResNet. So the first one starts with a 7x7 kernel followed by a max pool and then has groups of here 3 residual blocks with 2 weights layers in each block. Downsampling is indicated by these dashed lines between these groups of residual blocks, where after the first max pool, these are always performed by strided convolutions implemented for the first residual of the block. So this here represents a 34-layer residual net. The same paper proposed a 152-layer version, where it made use of these bottleneck layers, so layers with one-by-one convolutions going in and coming out, so as to first reduce the channel dimension for the more parameter-heavy 3x3 kernel operation, and then upsample the channels again in order to decrease runtime and the total number of parameters which need to be learned. Then, subsequently in 2016, the same authors proposed an updated version of the ResNet, which they found essentially through trial and error of different approaches to implementation of these shortcuts, where here they specifically recommended that, in contrast to the original network, the ReLU and the batch norm should act as pre-activations rather than post-activations of the convolutional layers. So this formulation was shown to increase performance quite well for very deep networks. So far the emphasis was on increasing depth, and this isn't entirely unsurprising because deeper networks support learning of more complex features with increasing receptive field size. At the same time, historically, it has been thought that as a rule of thumb, deep networks are more likely to generalize, whereas wide networks more likely to memorize, since we've already seen that even simple single-layer MLPs can act as universal approximators in principle. However, in doing so, they require exponentially more components than an equivalent deeper network, and so in doing so, they are just primed for overfitting. However, at the same time, to get appreciable boosts in performance, it was starting to require unsustainable increases in depth. For example, with each paper reporting a fraction of a percent of improvement in performance, it was starting to require almost doubling of the number of layers, and so this was making it a problem of diminishing returns. Therefore, for these reasons, the authors of wide ResNet instead proposed increasing the width of the networks through training more convolutional kernels, more channels for each residual block. They also added dropout units for regularization between the convolutional layers in each block, where, importantly, these orange blocks here are inclusive of the batch norm and ReLU. So these, as before for ResNet version 2, are implemented before each convolutional weight learning layer. Therefore, by increasing filters in each layer by a factor of 16 for the first group of residuals, 32 for the second group of residuals, and 64 for the fourth group, the authors of ResNet found it was possible to achieve equal performance using a 16-layer wide net as for a standard ResNet with 1,000 layers. So they're reducing the layers by 50 times and training twice as fast, but achieving equal performance. Then came DenseNet. So here, this extended on a standard ResNet by allowing skip connections or residual connections not only across a single block, but also across all subsequent blocks, which by contrast led to much thinner networks with fewer features learned at each layer. All the DenseNet residual blocks were implemented as bottlenecks, incidentally, and downsampling was performed with pooling rather than striding, noticing that this was occurring between these dense blocks, such that the feature map sizes were the same within each dense block so that they were able to be concatenated together easily. The network then finished with a global average pool and a softmax classifier. It was said that this architecture alleviated the vanishing gradient problem and strengthened feature propagation and therefore encouraged feature reuse. However, why focus only on increasing depth or width? One might also consider increasing the input image resolution, as this would provide greater detail in terms of textures and capture of smaller objects. But equally, why consider any of these parameters in isolation? So in 2019, a team from Google observed that scaling on one element of a network shape led to diminishing returns. So for example, if you train a ResNet with 1,000 layers, you don't gain a huge amount of performance relative to one with 100 layers. And similar observations were made for width and resolution. So in this paper, they therefore instead proposed a compound scaling method which, given optimized performance for some fixed number of parameters, uniformly scaled the width, depth, and input resolution to optimally make use of the available resources, achieve much informed performance relative to previous networks, and at the same time use far fewer parameters. So in summary, computational memory has increased vastly since the first CNN, but there remains constraints placed on network size by the total amount of data available to train with. So networks have been able to grow increasingly deep through implementing tricks such as bottleneck layers and inception modules in order to reduce the amount of parameters required to learn equally expressive multiscale filters. Also, residual connections, which have allowed networks to ignore deeper layers if it doesn't need them. Greater depth supports learning filters of greater receptive field size and expressivity. However, at some point, increasing depth just leads to diminishing returns, as with residual layers present, there's nothing forcing the layers to learn anything at all. Equally, increasing width increases the range of textures that can be modelled by the network at each scale, and increasing input resolution may provide the network with finer details in the first place. However, if you consider each of these factors in isolation, then performance quickly saturates. So EfficientNet was the first paper to propose uniformly scaling all three of these parameters together, and it proposed a compound scaling formula to support people in doing that. So that's it for this first lecture on classification and regression CNNs. Please attempt the Keats quiz before moving on to the next video.